Hello, my name is Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. Please subscribe. If you're a returning viewer, it is great to have you back. If you liked the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. And if you're watching this because you are having a hard time learning the concepts, please stay encouraged and positive. This video and all my other videos are meant to help you. So all that being said, let's go ahead and get started. So our previous video was about sample proportions in general, which is a very simple concept. This video will go a bit further and talk about sampling distributions for proportions. Now, a few things. We did this in an earlier video about sampling distributions for the mean. This is the same basic idea. Now, what that means is if we go out and collect a bunch of sample proportions and put those sample proportions into their own distribution, that's called a sampling distribution. And there are certain things about that that will help us learn more about our overall population. So let's go ahead and begin. So this video is brought to you by the great people at the Great Courses Plus. Chances are, if you're watching this video, it's because you are here to learn something. And there are few better places to learn anything than the Great Courses Plus. They have over 11,000 videos on anything from photography to literature to philosophy to economics and yes, statistics and math. So please follow the link in the description below where you can get a free trial that helps support this channel and of course the Great Courses Plus. So let's revisit our problem from the previous video. The administration at Caffeine State University, or CSU, is considering the addition of a late-night cafe to the student union called Moonlight Cafe. It will have drinks, snacks, comfortable furniture, and plenty of study space. To learn more about student interest, the administration hires 25 graduate students to go out on campus and survey 30 students each. Yes or no? Would you study at Moonlight Cafe at least once per week? If it can be estimated that about 60% of the student body would answer yes, CSU will go ahead with the project. So for the survey, 25 grad student workers are tasked with contacting 30 students to ask each of them demographic information and the primary survey question about the cafe. In the end, the researchers will end up with 25 samples each containing the yes or no responses for 30 students. The number of yes responses out of the 30 is the quantity of interest. So we will end up with 25 different samples. Each sample will be of 30 random students on campus. Now, a few points of note. There is no way to survey every student on campus. That would be the entire population of students. Therefore, the administration must take samples. And from those samples, the administration must then make inferences about the entire student population. That's the whole point of statistics in general and inferential statistics particular. We cannot go out and select every element or every piece of the population, in this case students. Therefore, we use samples to infer characteristics about the entire population. The inferences made using samples are by definition incomplete. Therefore, the sample characteristics will always have some error built in. So here is the data from our surveys. We have 25 student workers that all go out and ask 30 students if they'll use or study at the Moonlight Cafe. So the first sample here in the top left, 22 students out of 30 said yes. If we go down, 17 out of 30 said yes, 15, 14, 18, and so on. So here is our data. 25 samples, each containing 30 students, and the number here is how many students said yes. So here are our sample proportions. So in the first sample, about 73% or 0.733 said yes. In the second sample, about 57% said yes. In the third sample, half of them said yes, so 0.5. So here are our sample proportions, all 25 of them. So each of these represents one graduate student that went out and sampled 30 students. Now the mean of these sample proportions is 0.612. So remember, we're kind of looking at a proportion of about 0.6, so the mean of these samples is 0.612. So the standard deviation of these sample proportions is 0.0922. Now remember, since we have a sampling distribution here, the standard deviation of a sampling distribution is actually called the standard error. That's why I have it over there in parentheses. Now I went ahead and did another sample using some software, and we got a little bit different numbers. As you can see here, the mean was 0.589. That's pretty close to 0.612. The standard deviation, or the standard error, was 0.072. So they're not going to be the exact same. That's the nature of random sampling. There's going to be a little bit of difference in each sample. So while they're close, they're not exactly the same, and we'll talk more about that as we go forward. So here is our sampling distribution. We have 25 samples, and each sample has 30 students in them. So what we'll do is we'll go ahead and plot our data points in this sampling distribution. So we go ahead and do that, and we can see where each one falls within the sampling distribution. Now remember, using the empirical rule, we should expect about 68% of these data points to fall within plus or minus 1 standard deviation. So that's what we have here. And then we should expect about 95% to fall within 2 standard deviations, and then almost all of them within 3. And that's pretty much exactly what we have here. So if we do a histogram of all those sample proportions, this is what we get. And if we plot a marker at 0.6, which is right here, we should expect about half of our sample proportions to be above that and about half to be below that. And we obviously do. So you can see that over here on the left, we have 7 sample proportions in this first bin over here on the left. Then we have about 9, but a few less, okay, because the marker falls right here off to the right a little bit, off to the side. So not quite 9, maybe about 7. Now remember, we have 25 graduate students, so we would expect around 12 or so to be to the left of this gray line, and about 12 or so to be to the right, give or take 1 or 2. And that's exactly what we have here. So what about the expected value of P bar? So P bar equals the expected value of P. So P is the population proportion. Now, what we can say here in plain, but kind of riddle-like English, is that if we take many random samples from the population, in this case all the students, each with its own sample proportion, and then create a distribution based on all of those sample proportions, the mean of that sampling distribution is equal to the population proportion. So in this case, we had 25 grad students go out, survey 30 students. We put all the sample proportions in their own distribution. That's a sampling distribution. We took the mean of that sampling distribution, and we had 0.612, I believe, and that would be the expected value of P. Going out and taking many samples from the population and taking the mean of all those sample proportions. Now, what would or should we expect in this case? So our population proportion we expect to be 0.6 or 60%. So what we are saying is that we would expect on the long average, if we went out and surveyed 30 students, that we would expect 18 of them to say yes, and then we'd do it again. We'd expect 18 to say yes again and again and again and again. And over the long run, we'd expect to have on average 18 students out of each 30 sample to say yes. So what about the standard error of P bar, the sample proportion? So remember from the first video, this is our formula for the standard error. Pretty simple. If we go ahead and substitute all of our numbers in, what we end up with is a standard error of 0.8944. That's what we would expect sort of theoretically. Now remember, we got a standard deviation or standard error of 0.0922. That's very close to what we would expect theoretically to happen. So we should not be surprised by that. So let's look at some other cases. To do that, we will first look at the effect of the number of samples we take. So here's what we're working with. This is what we expect to happen. Now here is our first case. Now this is exactly what we did in our problem. We had 25 samples. Each sample had an N of 30. That's 30 students we surveyed. And then we're going to assume a probability of 0.6. So if we do that again, we get a mean of 0.60133. That's what we would expect to happen. Notice our standard deviation here, 0.0920. Again, that's very close to 0.08944, which is what we would theoretically expect down here at the bottom. Now let's take 100 samples. So instead of 25 grad students going out and each surveying 30 students, we're going to have 100 grad students go out and each survey 30 students. So look what happens. Our mean is 0.605 approximately. That's what we would expect. Our standard deviation, or standard error, what we're talking about here, is 0.084, which is very close to what we have down here at the bottom, what we would expect. But I don't want you to be confused by the standard error of the mean in these boxes. That's not what we're talking about here. We'll get to that in a second. But what we're looking at here is the standard deviation of these sampling distributions, because the standard deviation of the sampling distribution is the standard error we're interested in. Now what about 1,000 samples? So we have 1,000 grad students go out and each survey 30 students. So here again, our mean is 0.5992. And our standard deviation, or our standard error of the sampling distribution, is 0.09384. Again, it's pretty close to what we'd expect. So what about 10,000 samples? 10,000 grad students go out and sample 30 students. Now our mean is 0.599 again, and our standard deviation of the sampling distribution is 0.0901. Again, very close to what we'd expect. So what can we say about the effect of the number of samples? It's kind of a trick question because it doesn't matter. Notice that in our formula here, it's based on P and N. And in every one of our samples, N and P are the same. Therefore, the standard error is the same. Now, what about the effect of the number of samples? That does have an effect, but not on the standard error. That has an effect on the standard error of the mean of all of our sample proportions. So if you notice, the standard error of the mean is 0.018, then it goes down to 0.008, then it goes down to 0.002, then it goes down to 0.0009. That's because we're taking more samples, not because our sample size is changing. We're taking more samples. So what I wanted to show you with this slide is that as long as the sample size and the proportion are the same, the standard error is the same. So what we can do using a method called bootstrapping, and if you're not sure what that is, don't be worried. You don't have to know what that is. I'll kind of explain it as we go. Using bootstrapping, we can simulate these an absurd amount of time. So let's take 25 samples, each with 30 students, but we're going to take those 25 samples 1,000 times. Now, if you look down here in the summary statistics for the standard deviation, again, remember, which is the standard error, you see that the mean is 0.0889. Now, what are we expecting down here in the lower right? 0.08944. That's very, very close. Now, what about if we took 100 samples 1,000 times? What happens then? Well, look, we have a mean of 0.0928. Again, that's the standard error of our sampling distribution. So we're right around the same place. Now let's go crazy. We're going to take 1,000 samples 1,000 times. Now look at our mean for our standard error, 0.0863. We're expecting 0.08944. Very, very close. Now let's go crazily absurd and take 10,000 samples, each 1,000 times. So our mean for our standard error is 0.08944. What are we expecting? 0.08944. So what we did is we took an absurd number of resamples. We went in and took some sample, many, numerous times in this case. And when we did that out over the very long run, what we ended up with was exactly what our formula told us we should expect. So we matched experimentally what our formula told us we should expect. And you can see that they match exactly. So now let's talk about the effect of sample size on standard error. Remember, up to this point, every sample we've been doing was 30 students. Grad student went out, talked to 30 students, tabulated the results, and that's what we had for each sample. So here's what we've been working with. 30 students here in the denominator for the standard error. On the right, we have what we expect to get, which is 0.08944. Now what if we have each grad student go out and ask 50 students, not 30? Now our standard error is 0.06928. See, it decreased. Our standard error narrowed. What about 100 students? Now our standard error is 0.04899. See what's happening here? So as we increase the sample size for each sample, the standard error decreases. It narrows. So remember, comparing what we did before, where we just took more samples, each of the same size, 30, whereas here we're taking larger samples each time, 30, 50, and then 100. So if you want to decrease the standard error, the secret is to increase the sample size a bit, 30 to 50 to 100. And remember, that is the beauty of statistics, is that you do not have to increase the sample size to a crazy number to get the benefits of that increase. So here from 30 to 100, we almost cut our standard error in half. So just a modest increase in sample size can really decrease that standard error. So the expected value of the sampling distribution is at best going to be an estimate of P, which is the population proportion. We would have to take every conceivable sample from the population to match the population proportion perfectly. But if we do that, what is the point of sampling in the first place? The whole idea of statistics, or one of the main ideas, is that we make this a whole lot simpler by making inferences from samples we can collect easily. So the best we're going to be able to do is find an interval estimate for that population proportion. Our interval estimate will be influenced by sample size and the degree of confidence we are satisfied with. Those are topics for future videos. We did not get into confidence intervals for the proportion or anything like that, because to actually understand what the confidence interval is, we have to understand what the standard error is, because the standard error plays into what we use to determine the confidence interval. So we'll talk about confidence intervals for the sample proportion in our future videos. So stay tuned. This video is brought to you by the Great Courses Plus, where you can get unlimited access to over 11,000 video lectures taught by award-winning professors from the Ivy League and other top schools around the world. You can learn about anything that interests you: science, literature, photography, gardening, and yes, statistics, like this lecture from Professor Tim Chartier called Political Polls: How Weighted Averaging Wins, from his course Big Data: How Data Analytics is Transforming the World. Right now, the Great Courses Plus is offering my viewers a free trial. It is also now optimized for Australia and the UK. So go to thegreatcoursesplus.com/Brandon Foltz, my name, to have access to the over 11,000 video lecture library, or click on the link in the description below. So this video was the next in our series on sample proportions, where we talked about the sampling distribution for proportions and learned some interesting facts about if we increase the number of samples versus the sample size, what happens to our sampling distribution. So I hope you liked it. I hope you found some insights in it, and look forward to seeing you in our next video. Take care.